All right, cool. So we're going to go over kind of, I think, what's going to be the last chunk of code we're going to go over for the water quality project here. And I'm actually running this code right now on my machine. But we'll just kind of go through where we left off, which was, this is the code on GitHub. So we finished off last time looking at this whole loop here. So this whole loop here is where we were running, taking a number of subsamples for every iteration. So in this case, the way I have the code written here, I was doing 100, this is like 120 samples at a time, stream samples, and then we're running this, doing 1,000 iterations. And so the idea is that each time you're taking some number of samples across Southern California, you're splitting into training and testing. So 80% training, 20% testing. You're running a random forest model. And then we run the predictions. So predicting the CSCI using a model, testing how well it's correlated on the remaining 20% of the data, and then taking all of our evaluations and binding them together in one really large data frame. And then within that, what we're looking in is we're making all the data, basically all the XY coordinates for our top 10 variables in terms of relative importance. So this is where we're doing all the partial dependence plots and binding it all together. So we're making one giant data frame that is the analyte data. So let's say like nitrate or phosphate, and then the CSCI score that responds to it. And we're storing that all in one giant data frame. And that's where we left off. So now we have we have all of our evaluation and partial plot data frames. Where we are now is that with this line of code, we have our evaluation statistics. So this is where we did our correlations. So for the random forest model, we did an evaluation and said, okay, let's make the prediction of the CSCI score. Let's see how well it correlates with the other 20% of the data for each iteration. And this is for all 1,000 iterations now. And at this point, say, like, oh, let's filter out the ones that aren't significant. And the standard significance cutoff I'm just using is p less than 0.05, which basically means like there's 5% chance that this is what you're seeing is really due just to random noise. And then I'm just dumping that out, printing that out to a table just to save the significant correlations. By the way, one of the things that we're doing right now is that we're playing around with just increasing the number of samples for each run. So in this case, I was doing it at 120, but I'm increasing the number of samples per run to see at what point do we have enough such that every correlation we do is significant. So just to give you an idea, like the significance of the correlations, you tend to get a larger proportion of the correlations are significant if your number of samples is larger, because you're tending to build a more robust model. And so one of the things I've been playing around with is just like, okay, well, what's the minimum number of samples we need per run? My guess is probably around 180 to 200. So we're actually running that right now. But this is just a way of saving it. And then something else that would be of interest is looking at, okay, well, what's the average? What's these, if you were to say, well, what's, of your 1,000 runs, so you're randomly subsampling, let's say 180 samples at a time, you're doing 1,000 times, what's the average correlation strength? And you could try to justify saying, like, I'm just going to take the straight up average, but correlation coefficients, is you might think about this for a minute, they're not simply the same as just taking a straightforward number. It's taking like, okay, here's a model, here's how much the variance you can explain in Y given changes in X. So to do the average of it, there's different arguments about how you can do it. We're doing something that's based on, I actually included the citation here in the comments here, but there's an R function, it's called Fisher Z. And basically what it's doing is it's doing a transformation on the R, on your, let's say, Pearson correlation coefficients, so that when you take the average, it's more, you're actually doing a more meaningful calculation of what the average truly is, as opposed to just doing a raw average. So this is just saying Fisher transformation of the scores, take the average of it, and then convert it, do a Fisher inverse transform, so you can transform it back to something that like makes sense. So this is the average, this is the standard deviation. So basically these two lines here are to say, hey, out of your 1,000 runs for your models, how much of your, what's the amount of variance in the CSCI can you predict with your random forest models using the chemical analyte data? And this gives you the average, this gives you the standard deviation. So it's basically going to be, let's say, for example, it'd be like, this is 0.7 and this is about 0.2. Then you could say, okay, 0.7 plus or minus 0.2 is my Pearson correlation coefficient for running all these models. So that you can just give a straight up answer like, well, 70 plus or minus 20% of the variance can be explained this way. Some of the other stuff that we want to do is like, all right, if we want to look at the relative importance of the random forest models that we're looking at, remember, like we were calculating the relative importance for each iteration. But if you can imagine, like we have hundreds and hundreds of chemical analytes every time we run this. And so you're doing the relative importance, like you're going to have for each run, you're going to have a table that's like hundreds of rows long. And so most of them aren't going to be very important. And how do you handle all this? Well, what we're doing here is we're summarizing it. So we're saying, okay, like I have 1,000 iterations. So I have 1,000 relative importance tables. But what's like on average the relative importance of those for every 1,000 iterations for each chemical analyte, like, you know, copper concentration. So this is, there's a package called ddply in R. What it allows you to do is it allows you to do summary statistics across a whole data frame. So what this does is say, ddply, here's your data frame. So this is the huge aggregated relative importance table. It's saying, okay, now dot names, when you do this in ddply, it's saying, look at every variable you have. In our case, it's like hundreds of them. So, you know, each, you have like 1,000 instances where you have copper concentration, or, you know, the number of watersheds you're using. And then this is saying, okay, now summarize it. And then now this, at this point, we're just saying, okay, now calculate some new columns for our data frame. And this is going to be the mean. And this says include node purity. We're increasing node purity. This is how random forest models, when they evaluate the relative importance, they're doing this whole thing where they're looking at the node purity, which is a way of saying like the nodes in your random forest tree are where like each node is the variable in the tree. And so where it branches is basically pointing to like where you split on a variable. And this is just a way of saying like, if you were to remove that variable, how much does it influence the output of the model? And things that influence it greatly have a really high increasing node purity score. So it's just a way of calculating it. The hard number itself is not so much important as the relative. So basically bigger numbers compared to the other numbers you see are going to be more relatively important. So we're calculating the mean and the standard deviation on it, just to give an idea of like, well, okay, how important are these variables overall? And this is going to be important because we don't really want to look at all of these when we want to give some examples of like partial dependence plots, because there's going to be hundreds of variables and most of them don't really matter. We just want to do like the top, like, you know, handful of them. And so that's what these two rows here to do. And the col names, by the way, is just renaming the column variables, just so it's something easier to remember. And then we're dumping that out into a text file. Okay. So one of the reasons why we wanted to know what the importances were, because now we can go and we can calculate on this line here, which is what are our important variables. And in the R package dplyr, there's actually a function called top n, which basically just says, give me the top whatever most important numbers, or like the largest. So this is saying like, I have my data frame, take the top 10 here, given my mean increased node purity. and then we'll extract that information. And so what this is saying is like, all right, this will give us the top 10 most important. So we may change like which number we want to play around with on this, but for right now, we're just doing like kind of the top 10 most important. And once we have that, now we can go in and actually start generating all the plots. So this is saying for model variable and important variables. So when you do a for loop, it's just like, I've got my list of important variables here. It's gonna be like 10 long. And this is saying like, all right, now let's loop through all those 10 most important variables. And now what we want to do is we want to go back and take that huge data frame we built, which was like all the partial dependence data. So essentially like, oh, if I vary copper, what happens to CSCI? If I vary the year, what happens to CSCI? So it's going to be a huge data frame. What this is doing is like, all right, now only select one variable at a time, and we're only going to do the most important ones. And a way of grabbing that is going to be, here's your big data frame. Now we're going to subset it. And again, we're to the right of the comma. So now we're only subsetting based on columns. And we're using this function here called grep. And grep is one of these search commands. So basically it's like literally like look for things. And it says, all right, grep. And now we're looking at this thing here. Paste is just a command that takes all this and it strings it together. So now you're going to have a new string that's going to be caret, the name of the model variable, followed by the $sign. And then there's no separation between them. So we have this string here, and it's going to be whatever variable we happen to be looking at the moment. Grep means search for things using this particular string. And this seems really cryptic if you've never used grep before. But what this is saying is that this up arrow thing means only look for stuff where it starts with the variable name. And then the $sign means ends with. And the reason I wrote it this way is that we're only looking for things that specifically have the start with and end with, because we're only looking for things that exactly match the variable name. So like, let's say copper concentration. And because there are things, for example, like chloride and chloride dissolved, and you want to distinguish the two. So this is just saying starts with, ends with, so we're only doing an exact match. And then we're doing, this is for the first column. And then for the second column, it's that we want to subselect, it's just starts with CSCI and then ends with the variable name. Because the way we've done this is that we have the variable name and then the response in our partial dependence plots is CSCI space the variable name. And so what this is just doing is saying, all right, get the variable, get its response. And that's what these two lines are essentially doing, is extracting from that data frame just those two columns from your gigantic partial dependence plot data frame. So just to remove, because there's gonna be a lot of like NAs, like just empty cells in there, you wanna remove those so you don't have a bunch of blank rows, because they come along for the ride, like given how we've calculated this, you don't want them. So to remove them, there's a thing called complete cases. It just removes like the empty rows and columns. Okay. Now we have RF total, which is going to be our partial dependence plot for a particular variable. And it depends on which plot we're going to make, depending on what kind of data type we're looking at. If you're looking at something that's a categorical variable, so like watershed is our categorical variable that we're looking at. And by categorical, I mean like you can't plot a number value to a watershed. It's like it is a value like LA, Ventura, so on. It's just a category. And if you do that, we make something called a box plot. So this here basically says if RF total, that first column, which is our variable, so it could be watershed, if it's categorical, make a box plot, and this is the syntax for it. And there's all these things I played around with, your parameters, like how you want to angle the text, how big you want to make it, all that sort of stuff. And if you do that, you get something that kind of looks like this, which is, hold on a second. All right, so if we do that, you get something that looks kind of like this, which is a box plot, which is like each watershed and the modeled response and the CSCI scores, so there's a big variation in it. But this is where what it looks like. So it's saying the model predicts If I'm in Cayugas or Santa Monica Bay, I'm going to have a relatively low modeled CSCI. If I'm in San Gabriel, Santa Clara, it's going to be higher. So that's what it's doing in that first chunk of code. The second chunk of code is this, and this is saying not a box plot, but we're going to do something called geombin D2, or 2D, sorry. And this is making what's known as a two-dimensional histogram, which is that whole heat map thing. And it's saying, okay, now in this case, now you're going to plot a heat map where you have 1,000 response curves, but you want to make a plot where you show in each pixel in the plot, how often does it pass through that point and color code it. So you can get a general idea like, well, we're running this 1,000 times, but the model more or less goes through this sort of trajectory. And you get a plot that looks something like this. Yeah, so this is an example. Let me show you one that looks a little cleaner. There we go. So you get something that kind of looks like this, which is, we ran this 1,000 times. Out of those, like, 700 of the times, for example, every predicted curve goes through there. Maybe like 500 times on average it goes through there. So you get a general idea. We ran this 1,000 times. You start to get an idea of like, oh, where do things fall? Now, this pink curve here, which is also part of that code, gives you a general fit. So it's saying like, okay, this is just overlaying every model on top of each other. This is saying on average, what's the trajectory? And the trajectory is really boring looking. It's just in our case, it looks basically like just a downsloping line. It doesn't need to be linear. We can have plenty of things that look non-linear. Let's see what it looks like here. Yeah, it looks kind of the same. There might be a non-linear one in here. Wow, they're really all that boring. Okay, hold on. Nope, all right, never mind. So in our case, I guess it is really going to be that boring. Sorry. So this is just sort of the general fit. And so we're doing all that. This gives us our plots, and we're going to end up generating 10 plot objects. And what we're doing then is we want to get a list of all those. And we do a thing called ls, which is just literally the list command. R is kind of like Unix like that, where you can just say list. In this case, it says, okay, list, but only give me the list where I have pattern where the name of the object is rfplot. And this is a wildcard. This literally like parentheses dot asterisk question mark, close parentheses, is just saying like something. It's just a wildcard. So it says rfplot something. In our case, it's going to be some sort of number. This is like how we're naming things, followed by iterations, followed by something, in our case, a number, followed by samples, panel, again, another number. So it's saying just give me everything that follows this pattern. So it's going to give you the 10 plots you've generated. And then what we're going to do is we're going to take all that list of plots. We're going to convert it to a merged object using a command called mget, which is actually a base R function. And then once we have all of that, so we're making this RF plots total is just like saying, all right, import all of these objects into a single like variable. And then when I run this other command, this is another base R function called invisible, matrix apply. And then it says, all right, gg save file. And the file name is just going to be the name of each plot object. So we're going to generate 10 separate plots and then plot that object. What's going on here is that this is actually running through, and it's essentially running in a single line. It's running a loop. And it's saying for every object in here, which we have 10, save them as a PDF. So we'll end up saving 10 PDFs. So one file for each plot. So, because otherwise we tried doing it as a multi-panel thing beforehand. It does some weird stuff with the formatting. And I don't know, it doesn't come out nearly as clean. So that's kind of just like the overview of the last chunk of code, which is, okay, we ran the models. Now, what do the partial responses look like? What are the summary statistics? So, Cool. Any questions on this?
I was just wondering about the invisible function and
Yeah.
just like how it runs through the RF plot list, like without having to like do a for loop or something.
It's more of the if you look at let me pull it up really quick. R invisible. So there's two functions we nested in there, but it's basically the invisible part. It says like we're actually producing a bunch of invisible copies of something. So in our case, it's like 10 plot objects, but we don't want to plot them. So it's a way of like because you can generate plots in R and it'll automatically output them. But what this is saying is like, don't plot them yet. We actually don't want to like print it to screen. We want to print it to file. So that's what the invisible part is for. The other part here where it says M apply, this is where, when you say apply, there's different types of apply, by the way. There's like L apply, S apply, and so on, but there's a whole class of functions called apply. And that's where you basically are running a loop without really running, like where you're not actually doing like for whatever. You're just saying, you're actually just telling it in one line saying like, do this and do this like multiple times. So if you just like look up map apply, you'll get there's different versions of it, but it runs over your list of arguments, and it actually does like the for loop in like one shot. So for the reason why like people will use the syntax, one is it's more compact, but when you get into parallel computing and try to running things where you split a job across multiple processors, you want to start using syntax like this, because this means that you can actually take your loop and then instead of like running in one processor, running something like 100 times, you could split it across 10 processors and run it 10 instances on each processor and be done in like a tenth the time. So that's where you start getting into like using functions like mapply, which is sapply, lapply, that sort of stuff. And it's like a little more advanced in R, but depending on what you're trying to do, if you're only doing like a few commands and you want to like loop over it, it's really great. For really complex things, like loops with a lot of like things you're doing in it, kind of like what we have, it doesn't really scale. So if you're doing a bunch of different commands within a loop, like it's not very practical to try to force it into there. But if you're just doing like something simple, like, hey, just dump all these objects into separate plot files, it works really well.
Okay, yeah. When you run it on like a multiple processors, do you have to like specify that later, or does it run through it normally?
You have to specify all that. So there's like a
Okay.
whole, yeah, if you want to like learn, like we talk about parallel computing at some other point, but there's multiple ways of doing it in R. You have to specify things like number of cores you want to use, how much memory you want to use, and then you have to be kind of careful with the system that you're working on. So depending on what computer system I'm working on, I do have to be careful with what kind of memory and number of processors I'm going to allocate. So for example, my computer has 4 cores. But if I'm running on a remote machine, I can probably get like 40 to 50 maybe. And so I can't necessarily write the code the same way. But there's like a whole host of like, there's actually like various packages in R to do parallel processing. And it takes a little more work getting used to. And some jobs don't parallelize really, like you actually have to do them sequentially. But then there's plenty of things where like, yeah, you can just like split it all up and it doesn't really matter. So things that you have to do in order, like you can't really get away with it. So.
Okay.
Yeah.
Sounds good.
Mm-hmm.
I was wondering actually, it was a while back for the functions, but I think it's in dplyr, the percentage greater than and then percentage, like that little function.
Percentage greater than. Oh, this stuff?
Yeah, I was looking it up, but does it just mean like do all these multiple functions in one line, or?
Yeah, so in deployer, this is like, it means pass to, pass to, pass to. So it's saying that it's, what you're saying is that, okay, like take your chemical data frame, pass it to this group function where we're going to group everything by the unique identifier, pass it to the mutate function where we're going to sort of split, instead of like, how we had it as a column where like each row is a different chemical, where each row is like a particular analyte, and then take that. So now we're taking that, like, we want to split those into columns, and it says, okay, now spread it. So now we're going to take that column with all the chemical analytes, flip it around. So now each analyte is a column, and then pass it such that we're going to just select all of them and then dump out the results. But basically it's like a way of saying pass to. So you don't have to save each intermediate step as a data frame. You're just like literally just saying like, okay, take this, pass it to memory, and then pass it to this next function, which then passes it to this next function. So you're not like saving it long-term in memory. You're just like passing it through really quickly.
Okay. Yeah, that makes sense.
Yeah, I remember like the first time I worked with it, and it looked really wonky to me, but yeah. But yeah, this is something that I learned how to do. Most of this, actually, pretty much most coding I've learned is from Stack Overflow. So I advise everybody watching this, like, you Google the error messages you get, or you try to, like, a lot of it is just becomes like, how do I figure this out? You'll end up like on Stack Overflow. So that's pretty much where I learned most of my coding. Oh yeah, so the simming error, this is S apply. So it's not like matrix like don't apply it as a matrix. This says apply as a string. So anyway, it's basically the same thing here, where it says apply this function where every column except the first one, make it numeric. So it just lists over and does it for every column. So the apply stuff is like really powerful because it means that for a lot of things you don't have to put in a for loop each time. Ooh. So anything else?
I'll probably go through the new code first, and then I'll probably have questions on that.
Okay, cool. Just heads up, like, don't running 1,000 iterations is going to. I mean, on my machines, I have a 4-year-old MacBook Air. If I'm running like 180 samples at a time, and I'm running like 1,000 iterations of it, it takes about 3.5 hours on my machine. So, just you can drop down the number of iterations if you just want to test stuff out. Like, just drop down the numbers.
Okay.
If you want to run it like relatively quickly, yeah.
So our output will be through your computer, like what you run, so it won't be through ours.
Yeah. So I don't know what what system you have, like the power of it, but I mean, I have a 4-year-old laptop, so.
Yeah, I think mine's older.
Oh, really? Oh, okay.
Yeah.
Well, all right then. I don't know then, but yeah, it's just it just turns to like a matter of time kind of thing. Like, you probably have enough memory to do it. It's just like, how quickly is it going to happen?
Mm-hmm.
Cool. You want me to stop this, or?
Yeah, sure.
Okay.
Yeah.